In this video, we investigate convergence or divergence of what's called a positive series. Infinite series sigma a sub n from 1 to infinity is called a positive series if all the terms in the sum are positive. We're going to use what's called a integral test to check a convergence or divergence of such positive series. Let's first have some idea how we come up with this test. If we plot those values in coordinate system, say A1, say A2, so let's just mark it here, A1, A2, so A3, A4, and so on. Now, the value of this sum is the sum of those guys. In the coordinate system, let's create a rectangle using the height A1 for the rectangle, using this value to create another rectangle. Well, this should be SY because this is like when n equal to 1, n equal to 2, so the width are all the same, n equal to 3. My drawing is a little off scale, but you understand. Alright, so the first rectangle, numerically the area of this rectangle is the same as A1. So value A1 actually represents the area of the rectangle. Similarly here too, this would be the second rectangle with the area A2 because it's height A2 times width 1, height A3 times width 1. So numerically, the way A1 actually represents the area here, A2 represents the area here. This way, the value of the infinite series actually is the same as the sum of areas of all those rectangles. Now, let's try to come up with a function whose graph goes through, say, all those points. What we can see approximately is this function would satisfy, well, at each location n would equal to a sub n, the way we construct f. Now what we can see is approximately the area of the region under the graph of f, say this. The same as the sum of areas of all these rectangles. There's a little difference depending on where the A1, A2, A3, A4s are, higher or lower, higher above the graph, lower below the graph. But approximately the area of the region under the graph of f of x from, say, even 0 to infinity will be similar to the value there. So if we do 0 to infinity f of x, that's improper integral, that would be the area of this red shaded region. So that should be close to basically the sum of areas of all those rectangles, which is our infinity series. Because of this, we can prove under some conditions, which is pretty simple. For example, a sub n decreases if a sub n is not decreasing, the series will diverge, not approaching zero. So, for example, and a sub n approaching zero is necessary anyway. So there are some conditions which we require just to make the proof simple. But basically, giving any infinite series with a general term a sub n, that's some expression in n. What we can do is to replace the n by x. Then we come up with our function. That's how we come up with our function. There are other ways to do it. This is the easiest way. For example, given sigma 4n over 5n squared plus 3, well, we kind of construct our function just like that. Replace n by x. So from the graph up there, we can tell approximately the value of this is going to be close to the value of this improper integral, say from 0 to infinity. Now, the values are not going to be different by much. We can, since we only care about convergence, divergence of the series, we can check out the improper integral like this, starting from any number, say from 10, which means we would just consider kind of this part. For our series, we're missing just a few numbers which add to a finite number anyway. Therefore, when we check the sum of the series, we can get a pretty much good idea here too, just by checking improper integral from any number to infinity. Our conclusion is, regardless where you start out, we can actually prove mathematically too. If this is a finite number, this will be a finite number. If this is infinity, this is going to be infinity. And that's our integral test. So, with some conditions, we can actually prove the following result, our integral test. Positive series, a sub n greater than or equal to 0. Positive series and improper integral constructed this way, either both converge or both diverge. You see, visually kind of makes sense, but we can actually prove it mathematically. The function in the improper integral is constructed by simply replacing the integer discrete variable by continuous variable x. So with this test, want to check whether this guy converges, diverges, we just check the improper integral. If this converges, it's going to converge. If this diverges, this is going to diverge. It's pretty simple. Alright, let's see an example. So this is a positive series. Now let's construct a related improper integral. Just the same structure, 1 over now x plus 1, the same power dx to infinity. Now what number should we choose? We choose any number. We choose 1, we can use 10, we choose 100, because the different number would only mean, like in our graph, we're checking this part. Whatever we're not checking will not matter at all as far as the convergence divergence is concerned, because this is always a finite. This part, no matter how many terms added up, is a finite number. So that's another fact. Convergence divergence of the whole thing. So it's the tail that's going to matter. This reading we just start from 4. Okay, so this is a improper integral. How do we evaluate improper integral? Well, the old-fashioned way is to remember to number 9, 4 to infinity, and we go 4 to b, that kind of thing. So 4 to b approaching infinity. Then we work out the integral first. So on the side, let's find the antiderivative. Do a substitution, u equal to x plus 1, du equal to dx. So this is a 1 over u to 4/3 power du. Now apply the formula. It's 1 over 4/3 plus 1 u to negative 1/3, 1 plus that. This is negative 1/3, so it's a negative 3. The 1 over u to 1/3, or negative 3 x plus 1 to positive 1/3 power on the bottom. So that's antiderivative, and then we plug in b for x, 4 for x. So in our limited expression, it's negative 3 b plus 1 to 1/3 minus, it becomes plus, this is negative 4 plus 1, 1/3. Now we're saying to be to infinity. This is going to be infinity, this term becomes 0, so this is a finite number, 5 to 1/3. It's less than infinity, which means the improper integral converges. Now, according to our test, both would converge or both would diverge. So since this converges, the series converges. So very easy to use. Let's see another example. Again, we construct an improper integral with x replacing n up to infinity. Now lower limit, we can choose any number. We choose say 1. Again, according to the way we evaluate the improper integral, we're going to go from 1 to b, send the b to infinity. Now, evaluate the integral on the side, basically find the antiderivative. do a substitution. U equal to 4x squared plus 5. Du equal to 8x dx. So this becomes u bottom x dx becomes 1 over a du. So 1 over a plural, 1 over u du, that's log. The antiderivative, well, let's get 4x squared plus 5 back. Then we come back to our main work. B plug in antiderivative for x, 1/8 log 4b squared plus 5 minus 1/8 log 4 times 1 squared plus 5. Now, this is a finite number. We don't really worry about much. It's like log 9, whatever. When b goes to infinity, this goes to infinity, so we basically have a log infinity. Log infinity is infinity. Check the graph. This is log. It goes up, keeps going up, approaching infinity. So this is like infinity minus a finite number. So this improper integral diverges. The answer is infinity. It's diverges. Now, according to our integral test, those two are supposed to either both converge or both diverge. Now, this diverges, then we can conclude that the series will diverge too. Now, from this, this test is very easy to use. From these two examples, we see whenever we have a positive series with the general term that we think we can integrate easily, so that's the integral test should be a good choice. Now, integral test is very useful, very important, because sometimes this is the only test that's going to work. Later on, we're going to learn many different tests. There are times integral test is the only one that's going to work out. So that makes this test really important. It's also important because with this test, we'll come up with another convenient test. It's called the P-series test. The test says this series, well, you can see why it's called the P-series. It's a p-th power of n. So the test says this series converges if the power p is greater than 1. It diverges if the power p is less than or equal to 1. Now, how do we prove this? Pretty much like how we work on our examples. We just investigate improper integral like that, and it very easily we can, well, x cannot be 0, so we'll start from 1. Just do that. You find the antiderivative, and we can see pretty clearly if p is more than 1, if we do antiderivative, then there's still positive power of x on the bottom left, because you're going to basically just subtract 1 when you integrate the power from the bottom. With the still power of x on the bottom, plug infinity is like 1 over infinity 0, so the answer will be finite. Well, if the power is less than or equal to 1, you can end up with positive power in your antiderivative. That's going to approach infinity. If p equal to 1, you get the log x. That's like log infinity. That's going to be infinity. So just pretty much is very easy work involved, you find the antiderivative, plug in, check the limit. So very simple. Okay, so anyway, we have this P-series test, which can be easily proven by applying integral test. Now this test is very important, very easy to use too. For example, I have square root n. Now you can tell it diverges because the power in this case is half, less than 1, diverges. Or sigma 5 over n to the third power. Now the power here, p equal to 3. More than 1 converges. Then you say, well, what about pi? The P-series test, the series is 1 on top. It doesn't matter. It's a factor. So you can constant factor you can pull out. So it's like 5 times that. So it doesn't matter what number you have, whether it's 1 or any other number. The test holds true. When this is converges, 5 times that converges. When this diverges, 5 times that diverges. So don't really have to worry about the constant of the time. Anyway, so this P-series test can be applied directly to check convergence divergence P-series. That's one use of this test. As a matter of fact, there's many other important uses. One of that is we can use this test to estimate convergence divergence of many other series, which is important in some of the work we'll do later on. Not necessary to draw definite conclusion, but have some idea. Just a head start. For example, if we have 2n squared plus 1 n to the third power minus 3n. Series like that. Say n start from whatever. It's not a P-series. It's a pretty complicated series. But since we know convergence of divergence of the series depends on the tail of the series, meaning depends on the terms in which n is very large. So what we need to really focus on is the tail of the series when n is large. Now in this series, when n is large, what we see is the 1 can be ignored. So we can just drop lower order term from the top. We drop the lower order term on the bottom too. So this would be what we see when n is very large, approximately. In other words, the tail of the series will be more or less like this series because we drop some terms. So roughly speaking, we can actually show too mathematically using one of our tests we'll learn later on. The convergence or divergence of those two series will be pretty much the same. So in other words, both will either converge or both will diverge. This allows us at least to have some idea on this for now. Just drop a lower term, we'll end up with a new series. We'll end up with a new series. Well, a lot of the time it's a P-series, like here. If you simplify, this is the same as sigma 2 over n. So you at least can get some idea for now. P-series, according to the P-series test, this one diverges because P is 1. So With this, we can probably guess for now. This should diverge too. But this is just to estimate. It's not a rigorous mathematical proof. We will introduce some tests later on to actually show, yeah, it's the case. But anyway, just want to explain to you some usefulness of this p-series test, which can be proved using the integral test we introduced in this section.